Welcome and study with Tanzania Institute of Education.
Hello, my student. My name is Advocate Joseph Mbuga. I'm a chemist teacher. Today, we are going to learn about general chemistry, a subtopic known as quantum theory. We are going to learn through guiding questions. So, welcome. Quantum numbers are numbers which are used to describe the characteristic of electron in an atom. And there are 4 sets of quantum number. Today, let me discuss the quantum number through solving different questions. The question number 1, state whether each of the following set of quantum number is permissible for an electron in an atom. If a set is not permissible, explain why. So, by using knowledge of 4 sets of quantum number, we are able to answer this question number 1. There are 4 sets of quantum number. The first one is principal quantum number. The second is known as azimuthal or angular momentum quantum number or subsidiary quantum number. The third one, magnetic quantum number, and the last one, spin quantum number. So by using knowledge of 4 sets of quantum number, we be able to answer this question number 1. So question number 1 are Roman 1, given sets n is equal to 1, L is equal to 1, ML is equal to 0, and MS is equal to positive 1/2. So account if these 4 given set of quantum number are permissible or allowable. So by using knowledge of 4 set of quantum number, n is equal to 1, specify shell number 1 or energy level 1, L is equal to 2, ML is equal to 0, MS positive 1/2. So in order to know this set given are permissible or not, consider the main principal quantum number. The main principal quantum number is n is equal to 1. It means that shell number 1 or energy level number 1 for any atom. So if n is equal to 1, L is equal to 1, it means that the value of L given from our questions is equal to value of n. So that value of L account the given 4 set of quantum number are not permissible. Why are not permissible? The reason is the value of L cannot be equal to n. Why cannot it be equal to n? Because the value of L range from 0 n minus 1. So the value of L for n is equal to 1 must be 0. So L, which are given is 1, account the given 4 set of quantum number are not permissible. Are not permissible because of L. Roman 2, n is equal to 3, L is equal to 1, ML is equal to 2, and MS negative 1/2. Let me account if these 4 sets of quantum number given are permissible or not permissible. For n is equal to 3, specify shell number 3 or main energy level number 3. The value of L is equal to 1. L is equal to 1 is correct. ML is equal to 2. Okay, MS is equal to negative. For that given quantum number, the given set of quantum which is not collecting is almost ML cannot be greater than 0. Why cannot be greater than 0? The value of 0 is equal to 1, but ML given is 2. So the value of ML cannot be greater than 1. Why? From expression which accounted the value of 0, the value of 0 for any given, the value of ML for any given 0, that value range from negative 0, 0, then positive 0. The value of ML range from negative 0, 0, positive 0. So the value of 0, the value of ML cannot be greater than the value of 0. So here, 0 given is 1, ML is given 2. So ML is equal to 2 is greater than 0 is equal to 1. So the set of quantum number given are not permissible because the value of 0 cannot be greater than value of L. Lemma number 3, N is equal to 2L1, ML0, and MS positive half, to account if these 4 sets of quantum number if are correct or not correct. N is equal to 2, L is equal to 1. The value of L is smaller than the value of N. So by using this expression here, the value of L for any given N should be smaller than L. So L is equal to 1 is smaller than 2. ML, of course, is smaller than the value of L. MS positive half. The given 4 set of quantum number are permissible. And the last, Lemma 4, N is equal to 2, L is equal to 0, ML 0, and MS negative 1. So use knowledge of 4 set of quantum number to account these 4 set of quantum number if are permissible. So for N is equal to 2, energy level number 2, or shell number 2, L is equal to 0. Okay, 0 is smaller than 2, which is the value of N. ML is equal to 0, exactly the value of ML can be equal to the value of L. MS given is negative 1. According to value of MS, the value of MS can be positive half or negative half. And the value of MS cannot be Whole numbers, or the value of MS cannot take the whole numbers. So the given 4 set of quantum number are not correct. Why? Because the value of MS cannot be a whole number or cannot take a whole number. The value of MS can be only positive half or negative half. Let me look on question number 1B. Question number 1B, Lemma 1, what maximum number of electrons may have the following quantum numbers? Lemma 1, N is equal to 4L3, ML negative 3. So in order to know the total number of electrons present in a given set of quantum numbers, you are supposed to use knowledge of quantum number. For N is equal to 4, L given is equal to 3, and ML given is equal to negative 3. So ML specify 1 orbital, and this 1 orbital, it has it has 2 electrons. Which one? Positive half represent 1 electron, and the negative half represent another electron. These 2 electrons occur in only 1 orbital, which is specified by -3. So if there are 2 electrons, so the total number of electrons which are present in a given set of quantum numbers are only 2 electrons. Question number 1, B Roman 2, n is equal to 5, L is equal to 3. Determine total number of electrons present in a given set of quantum number. For n is equal to 5, L is equal to 3, the value of L is equal to 3 range from -0 to +0. Should range from -3 to +3. So these indicate total number of orbitals which are present in L is equal to 3. There are 7 total number of orbitals. To get total number of electrons in a given 2 set of quantum number, take 7 number of orbitals multiplied by 2, because 1 orbital accommodates 2 electrons. So total number of electrons which occur in a given 2 set of quantum numbers are 14 electrons. Question number 1 is C. Write the value of L and M for n is equal to 4. Let us start with the value of L. N is equal to 4. The value of L for n is equal to 4 range from 0 dash 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 n minus 1. So the last value must be n minus 1. So here the value of n is equal to 4. So 4 minus 1 is equal to 3. So the value of L for given n is equal to 4 range from 0 to 3. These values are 0, 1, 2, 3. These are value of L for n is equal to 4. So value of L can be obtained by using value of L. And the value of L can be obtained by using this expression, range from -L dash 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 0 dash 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 +L. So for value of L obtained from n is equal to 4, L is equal to 0, the value of L should be 0. For L is equal to 1, the value of L range from -1 to +1. And for L is equal to 2, the value of L range from -2 to +2. And the last value of L is equal to 3, range from -3 to +3. For question 1C, Roman 2, write all orbitals, or sometimes known as subshells, for n is equal to 3. So for n is equal to 3, to obtain number of, or to obtain orbital subshell, you are supposed to consider the value of n. So the value of n determines number of orbital, kind of orbital which are found in a given shell. For example, for n is equal to 3, it means that shell number 3 should have 3 subshells. 3 subshells. And these subshells are 3s, 3p, and 3d. So the kind of orbital for any given n determined by the value of n. So for n is equal to 3, there are 3 subshells, or 3 orbitals. And the last question, Roman 3, write total number of orbitals for n is equal to 3. For this question, Roman number 2 asks you to mention orbital subshell of n is equal to 3. But for Roman number 3, you are supposed to find the total number of orbitals for n is equal to 3. So in order to obtain total number of orbitals by using this tabular form, for n is equal to 3, the value of error should range from 0 to n minus 1. So the value of error for n is equal to 3 range from 0 to 3 minus 1. So the value of error for given n is equal to 3 are 0, 1, 2. The value of error for any given value of error range from negative error to positive error through 0. So the value of error for error is equal to 0 is equal to 0. And the value of error for error is equal to 1 range from negative 1 to positive 1 through 0, which are negative 1, 0, positive 1. And for error is equal to 2, the value of error range from negative 2 to positive 2, which are negative 2, 1, 0, positive 1, positive 2. Error specify number of orbitals for given value of error. So error is equal to 0 have 1 orbital. Error is equal to 1 have how many orbital? 1, 2, 3. And for error is equal to have how many orbital? 1, 2, 3, 4, 5. So the total number of orbital for n is equal to 3 are 1, 2, 3, 4, 5, 6, 7, 8, 9. So for n is equal to 3, the total number of orbital are 9. By using knowledge of 4 sets of quantum numbers, you have an ability to answer any question you'll be asked. For example, this question number 1, which asks you to know that or to identify which orbitals are correct or not correct, to determine number of electrons for any given quantum number, to determine number of electrons for any given quantum number. So now let me proceed to question number 2. Write electron configuration of atom having last electron filled in the following quantum number. So the electron given is a last electron filled in the following quantum number. N is equal to 3, L is equal to 1, M1 is equal to 1, and MS positive half. So in order to write that electron configuration, consider the knowledge of 4 set of quantum number. A electron of an atom distributed in an atom in order of increasing energy level, or electron arranged in atom in order of increasing energy level. So electron should be filled first in the first shell before second, and filled in the second after the first shell is fulfilled or completely filled by number of electrons required for first shell. So for this question, the electron given is a last filled in shell number 3, subshell L is equal to 1, which is P, ML positive 1, third number of orbital, and MS positive a half. So for n is equal to 3, it means that the last electron occur in shell number 3. So electron cannot be filled in atom starting with the shell number 3. No, electron must be filled first in the first shell, second shell, then in the third shell. So let me find the total number of electrons in the first shell, number of electrons in the second shell, and the total number in the third shell. For first shell, n is equal to 1, the total number of electrons which can be filled should be obtained by using this expression, 2n power 2. So n represents the value of shell. So for first shell, accommodate 2 electrons. Second shell, accommodate 8 electrons. And the third shell, the electron filled in L is equal to 1, M 1, and MSC positive 1. So if n is equal to 1 have 2 electrons, n is equal to 2 have 8 electrons, and n is equal to 3, you are supposed to use a table which can enable you to obtain that total number of electrons. For example, for n is equal to 3, electron filled in L is equal to 1, L is equal to 1, this one. And in L is equal to 1, the electron filled in ML1, which is positive. So ML, which is positive 1, this one. And in this orbital, the electron which is required is positive a half, so indicating this 1 electron. So for n is equal to 3, let me count this number of electrons from L is equal to 0 up to L is equal to positive 1 for this electron which have positive charge. So n is equal to 3 have how many electrons? 1, 2, 3, 4, 5, 6, 7. So for last shell which occur in n is equal to 3, the total number of electrons in shell number 3 are only 7 electrons. So to get total number of electrons which can be accommodated by this element, you are supposed to take 2 plus 8 plus 7, which is equal to 17 number of electrons. So light electron configuration of this element given by using 17 electrons. And don't light electron configuration by using only electron obtained from shell number 3. Why? Electron filled in an atom in order of increasing energy level. So it should be filled in the first, second, and then third. So from these two shells, the total number of electrons is equal to 17. So let me light electron configuration of 17 electrons. And remember, there are two kinds of electron arrangement, or two kinds of electron configuration. There is in terms of orbital, and there is in terms of box. So in terms of orbital, these 17 electrons can be shortened by using noble gases which have atomic number nearly to 17 electrons. So noble gases which have atomic number which is near to 17 number of electrons is neon. So it should be shortened by using neon noble gas. After neon, distribute the remaining number of electrons. Take 17 minus 10. Only 7 electrons remain. So must be filled in the outermost shell. And the outermost shell is 3s and 3p. So s orbital accommodate 2 electrons, and the p orbital accommodate 6. But in order to complete the arrangement of 17 electrons, 10 plus 2, which accommodated by s orbital, indicate 12 electrons. Among 17, only 5 remain. That 5 electrons remaining should be filled in 3p. So these are electron arrangement in terms of orbital and electron arrangement in terms of box. Okay, question number 2b. Briefly explain why chromium and the copper have unusual electron configuration. Okay, we know how to light electron configuration by using 4 sets of quantum number or value of quantum numbers. So let light the electron configuration of copper and the chromium, which expected. So chromium has atomic number 24. So atomic number 24 can be shortened by using noble gas having atomic number 18. So 18 electrons already distributed and arranged in the chromium. Among 18, there is 6 electrons which remains, should be filled in the outermost sub-energy level, which are 4s2 and the 3d4. This is expected electron configuration of chromium. And the copper having atomic number 29, the noble gas which can be used to shorten should be argon. The remaining 11 electrons should be filled in the outermost sub-energy level. So 4s accommodate 2 electrons and the 4 and the 3d accommodate 9 electrons. So these two are expected electron configuration of chromium and the copper. And the written according to the knowledge of quantum numbers. So to account the unusual electron configuration of these two elements and to light actual electron configuration, the chromium shortened by noble gas and the 4s accommodate 1 electron, 3d accommodate 5. And the for copper shortened by using noble gas known as argon, outermost energy level, 4s accommodate 1 and the 3d accommodate 10. So these are unusual electron configuration of chromium and the copper. The unique or unusual electron configuration of these two elements attributed by one principle known as half and fulfilled law. This principle accounts the unique or unusual electron configuration of these two elements, chromium and the copper. For chromium and the copper having unique, discovered that for P, D, and F, if these orbitals are half-filled, for P, 3, for D, 5, and for F, 7, are stable electronic configuration. And if these orbitals are fulfilled, P fulfilled 6 electrons, and the D fulfilled by 10 electrons, and F fulfilled by 14 electrons, are stable electron configuration because having minimum energy content. So according to half and the fulfilled rule, for chromium and the copper, 1 electron from s orbital or 1 electron of s orbital filled in 3D. For chromium, in order to have half filled orbital, which is stable, and for copper, 1 4s electron filled in 3D, in order to have full filled orbital, which both two orbitals are stable. Both two orbitals are stable. And the result, these two elements to have an unusual electron configuration or unique electron configuration, which disobey one principle of filling electron in the orbital known as the Aufbau principle. Question number 2C. Name the orbitals described by each of the following sets of quantum numbers. Roman 1. N is equal to 4, L is equal to 1. N is equal to 4, specify shell number 4 or energy level number 4. And L is equal to 1, specify P orbital. So orbital which described by n is equal to 4 and L is equal to 1 is 4p orbital. Roman 2, n is equal to 2, L is equal to 0. Which orbital described by these two quantum numbers? N is equal to 2, specify or describe shell number 2. And L is equal to 0. I think you know, specify S orbital. So orbital described by n is equal to 2, L is equal to 0 is 2s. Roman number 3, n is equal to 6, L is equal to 3. N is equal to 6, specify shell number 6. And L is equal to 3, describe the F orbital. So n is equal to 6, L is equal to 3, describe 6 F orbitals. Roman number 4, n is equal to 3, L is equal to 1, and ML negative 1. Identify orbital described by these three given set of quantum numbers. N is equal to 3, specify shell number 3. L is equal to 1, specify p orbital. But ML is equal to negative 1. P orbital have 3 total number of orbital. P orbital have 3 total number of orbital. So these 3 orbital specified by using orientation of p orbital. And the first orbital specified by px, second py, third one pz. So from Roman number 4, ML is equal to negative 1. So this, or the value of this orbital represented negative 1, this one is 0, and this one positive 1. So orbital described by these 3 quantum numbers is n is equal to 3, represent shell number 3, L is equal to 1, represent p orbital, and ML negative 1 represent orbital which is specified is px. So the orbital described is 3px. Is 3px. Last question. Question number 2D. Give the value of the quantum numbers n, L, and ML for the electron with the highest energy in sodium atom. Okay, we know that atoms have energy level, and if atoms have energy level, that energy level have different amount of energy. So electron filled in the atom in order of increasing energy level. Filled first in the orbital or shell of lowest energy, then filled to the next orbital of highest energy. So question number 2D asks you to assign quantum numbers of electron with the highest energy in the sodium atom. So electron of highest energy in the sodium atom should be electron which filled in the highest energy level. So in order to identify the highest energy level in a sodium atom, let's write the electron configuration of sodium. For sodium having atomic number 11, the electron configuration can be shortened by using noble gas known as neon. And the last one electron should be filled in the outermost subenergy level S. So the outermost subenergy level of sodium is 3s. And the electron filled in 3s have highest energy. So let's use these 3s orbital of sodium to determine the quantum numbers asked. Quantum number 1 asked is n, so n must be equal to 3, which obtained from subshell 3s. Arrow representing shape of orbital, and here for sodium the outermost shell, or the outermost shell is shell number 3, subshell 3s. So arrow for s orbital is equal to 0, or represented by 0. M arrow. Almost s orbital have only one orbital, and that orbital can be represented by value of arrow, which is 0. So arrow for this electron of sodium, which having highest energy level, is 0, because s orbital have only one orbital, and then represented by arrow, which is equal to 0. So these are 3 set of quantum numbers of electron of sodium, which having highest energy, or which located in the highest energy level in the sodium atoms. Problem number 3, or question number 3, arrange the following electrons represented by the following set of quantum numbers in the decreasing order of energy. Roman 1, n is equal to 4, L is equal to 0, ML 0, and MS positive a half. Roman number 2, n is equal to 3, L 2, ML 0, MS positive half. Roman number 3, n 3, L 1, ML 1, and MS negative a half. We are supposed to discuss arrangement of this given orbital in order to arrange in order of decreasing energy. So for n is equal to 4, L 0, ML, and MS are positive a half, identify what kind of orbital represented by these 4 set of quantum numbers. So for n is equal to 4, it means that indicate it is shell number 4. L is equal to 0, specify s orbital. For Roman number 2, n is equal to 3, specify shell number 3. L is equal to 2, describe sub shell D. For Roman number 3, n is equal to 3, specify shell number 3. L is equal to 1, describe subshell P. So these are orbitals represented by given 4 set of quantum number. So let's arrange this orbital in order of decreasing energy level. In order to arrange this orbital obtained from given 4 set of quantum numbers, you are supposed to remember the series which applied to light electron configuration, because the electron configuration is an arrangement of electron in order of increasing energy level. So that series can be obtained by using orbital of each shell. For example, shell number 1 have 1 s, shell number 2 have 2 subshell, shell number 3 have 3 subshell, S, P, and D. Shell number 4 have 4 subshell, S, P, D, and F. Use this orbital to construct a series of orbitals which apply to light electron configuration. So the first shell which have the first subshell which have lowest energy level is 1s, then followed by 2s, then 2p, 3s, 2p, 3s, then 3p, 4s. use this series of subshells or orbital applied to light electron configuration because electron field in this subshell in order of increasing energy level. So 4s indicate is highest energy level than 3p, and the 3p is highest energy level than 3s, and the 3s is highest energy level than 2p. So from given this orbital, there is 4s, there is the 3p, and they are supposed to include the 3d. So 3d should be written after 4s, 3d, then 4p. Then 3d indicate is a highest energy level or subshell of highest energy than 4s, and the 4s higher than 3p. So to arrange these three orbitals, we are supposed to start with the 3d, which is highest energy level than 4s and the 3p. Then 4s, which have high energy than 3p. So this will be arrangement of subshell or arrangement of orbital in order of decreasing energy levels. Question number 3b, deduce position of an element with atomic number 33 in the periodic table. We are supposed to identify the position of this element in the periodic table. In order to identify, we are supposed to use electronic arrangement of this element, but not atomic number. Use electronic arrangement. So let's write electron configuration of element having atomic number 33. Noble gas, which is nearest to 33, is argon. The next outermost subenergy level for filling the electron left include 4s, 3d, and 4p. So by using this electron configuration of this element, let me identify the position of this element in the periodic table. The position in the periodic table, we are supposed to indicate the period of this element and the group of this element. So let me start with group of this element in the periodic table. In order to identify the group of this element in the periodic table, we are supposed to determine total number of electrons in the outermost subenergy level or outermost subshell. For example, this element having atomic number 33, having this electron arrangement, the outermost or the subshell which occur after noble gas, there are 4s, 3d, and 4p. Among these three subshell, let me identify which one is outermost. I think here there is 4, 3, and 4. Can you tell me which one among these, which is almost outermost? On looking the value of this number, indicating the outermost subshell is almost subshell 4s and 4p. So the outermost shell of this element is shell number 4. That outermost shell having how many total electrons? 4s orbital have 2 electrons. And another outermost subshell 4p having 3 electrons. So 2 plus 3 is that our element to have the total number of electrons 5. So if having 5 outermost electrons in the periodic table should be grouped in the group having 5 valence electrons. That group in the periodic table is known as group 5A. Group 5A. For period. By using the given electron configuration, period, we are supposed to know the outermost shell. Here, there is 3 sub-shell, which are outermost, occur after noble gas. There is shell number 4, shell number 3, shell number. So the outermost shell here is shell number 4. The number of period is equivalent to number of shell. So if you have 4 shell, indicate this element occur in period, in the period number 4. Because here there is outermost shell number 4. So the period of this element in the periodic table is a period number 4. This is a position of element in the periodic table having atomic number 33. Question number 3C. Find total number of electrons in the principal quantum number n is equal to 3 by tabular form. We know how to find the number of electrons by using given expression known as 2n power 2. This applied to find the total number of electrons from any given quantum number, 1, 2, 3, 4, and etc. But this question asks us to find total number of electrons not by using this expression. We are supposed to use a table. So by using a table, we are supposed to have a knowledge of 4 sets of quantum number. N is equal to 3, principal quantum number 3. Have how many value of error? Value of error range from 0 to n minus 1. So value of error for n is equal to 3 are 0, 1, and 2. Then the value of error applied to determine the value of M error. The value of M error range from negative error to positive error through 0. So the value of M error for error is equal to 0 is 0. And the value of M error for error is equal to 1. Range from negative 1 to positive 1 through 0. So the value of M error for error is equal to 1 are negative 1, 0, and the positive 1. And the value of M error for error is equal to 2, range from negative 2 to positive 2. So the value of M error for error is equal to 2 are negative 2, negative 1, 0, positive 1, and positive 2. M error indicate total number of orbital. Total number of orbital. So the total number of orbitals for n is equal to 3 are 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. To get total number of electrons, we are supposed to take this total number of orbitals multiplied by 2 because one orbital accommodates maximum 2 electrons. So 9 times 2 is equal to 18. Therefore, the total number of electrons for n is equal to 3 is 18. I hope you have understood the concept well. Use the same concept to answer the following question.
Let's study, be educated, elimu ni kazi.